This problem is going to discuss the solution to the frozen food problem in the course packet. So we work for a company that prepares and distributes frozen foods, and we claim to put 14.5 ounces worth of stuff in our frozen package. We've just produced a bunch of frozen dinners, and we'd like to be able to estimate whether we're putting the correct amount in. So we draw a sample. We draw a random sample of, it turns out to be 11 frozen food packages that we produced. We weigh them, and here are the results. So part A asks us to identify the hypotheses to test whether or not your claimed weight is correct on the average today. So a couple really important points with this. Number one is we need to identify what is the parameter that we're studying here. So I scribbled it down on the pad over here. So let mu, oops, I think I've made this upside down. Let's get this right side up. How's that? Mu is going to be the true mean weight of all the packages produced today. So all packages produced today is going to be the population. The parameter is the mean weight if I could weigh all of those packages. All right. Now, another really important point about this is the way the question is asked is not directional. So sometimes you'll get a question that says something like, test whether the true mean weight is, or whether the observed weight is less than what's claimed. All right, not the observed weight. The average weight of all the packages today is less than what we've claimed. That would signal that you have a one-sided test. In this case, we haven't been given a direction. It just says test whether or not it's equal, and therefore the alternative is going to be specified as a not equal. So mu could be greater than, could be less than, we're not really sure. Okay, part B. Go estimate the mean weight that you would have found if you'd been able to weigh all the packages. So that's if I'd done a census of all my packages today. So let's go over to R and do that. And so if you type in mean of food, you'll notice I just entered in all of my 11 observations. So the mean weight of my 11 sample packages is 11.34, and that's what I typed up in the course packet. Part C, find a 95% confidence interval for the mean weight of all packages produced today. Before we can do anything that requires the t-distribution, we should note that we have a pretty small sample size, and the t-distribution requires a normal distribution. So we should really check and make sure that this data is at least approximately normal. So the way to do that in R is to do a normal probability plot. So if I say QQ norm food, I get the normal QQ plot. If I do QQ line food, it will superimpose a line in it. And what we see is that all the points roughly fall in a line, which suggests that the cumulative distribution for the observed data increases at the same rate as with a cumulative distribution for a normal distribution. So we don't question normality here. It's entirely plausible. I think it's also a good idea to always look at a histogram. And so there are no issues with this, no outliers, no problems. I tend to look at a box plot also, and we see roughly the same thing. So I think the easiest way to do this is with the t-test command. And all I do is type t-test food, and what you'll get is a 95% confidence interval for the mean. So 14.22, all right, it looks like I rounded correctly when I looked at that, but it is 14.23 to 14.45, and that's the correct answer. You could do this by hand if you want. So this is what I mean by doing it by hand. It would be the mean of food plus, and then to do plus or minus, I usually just do this, give it a vector of -1, +1, times, let's go find the 90.975% percentile of a t-distribution with 11 minus 1 degrees of freedom, times the standard deviation of food over the square root of 11. And so we get exactly the same answer if we do that. So we've just done part C. Part D asks whether there's a significant difference between the claimed and actual weight for today. Justify your answer. So one way to do this is simply look at whether the reference value, so 14.5 is called the reference value, whether that is contained in the 95% confidence interval. And notice it's not. It's just outside of it. And therefore, we would reject the null hypothesis that the mean is 14.5. Now, another way to do this would be to go back to t-test, and you can specify a reference value here. Now, if you don't remember what the exact option is, go to a question mark t-test, and you will see that you can specify it as the parameter mu. So let's go do that. So I'm going to go bring back my t-test command and say mu equals 14.5. And so now what you'll see is that we're going to test the alternative hypothesis that the true mean does not equal 14.5. We get a p-value of 0.00912. Now that p-value is less than 0.05. So 0.009 is what I wrote, 0.009 is what it is. And so since that p-value is less than 0.05, we're going to reject H naught. I actually think there's some benefit for me drawing a picture of what's happening here. So let's go over to the picture. This is the sampling distribution of X bar. And the first thing we always do when we test a hypothesis is we assume the null hypothesis is true. So under the null hypothesis, the mean of this distribution is 14.5. Now, we've gone off and observed a mean of 14 point, I better go, I don't remember what it was, 14.34, I think it was. Yeah, 14.34. And we need to go find the area in that tail. So that tail, as well as a symmetric tail on the other side, gives us the p-value for a two-sided test. So this is a two-sided p-value. So how do we find that? What is the probability of observing an X bar less than 14.34? Well, this is just going to be the probability that I observe a t statistic that is less than 14.34 minus the mean. Well, what's the mean? It's 14.5. And I need to divide by the standard deviation of X bar. So that's going to be S over root 11. And this number right here was actually given to us. It's this t statistic minus, so this whole thing is minus 3.2235, minus 3.2235. Now, let's just go back to R for a second and compute this. So if I say 13.34 minus 14.5, and I'm going to divide that by the standard deviation of food over the square root of 11. Notice I get minus 3.22 something or other. Now let's go find the tail probability, and I do that with PT. So PT, and I have 11 minus 1 degrees of freedom. So the tail probability is 0.00456. I'm going to go write that in, 0.00456, 0.00456. So to get the two-sided p-value, what I would do is take this number and multiply it by 2, since I have two tails, and that's exactly what the t-test function did. So in real life, I would just use the t-test function, but I think it's good for you to know how to do it by hand, if you will, as I have here. All right, that's it for the fast food problem. Not the fast food problem, the frozen food problem.